Yeah, I'm just joining the Zoom right now. Cool. Can people hear me through Enrico's computer? Yeah, okay, cool. It's okay. Um,
I can mute myself. It's
or
better.
it's fine as long as people can
No,
hear.
it's working. It's working well.
Okay.
Okay, cool. So as Manu has mentioned, Notion is becoming expensive and annoying to work with. And so as an alternative, we're going to use just a very simple bare bones wiki, just like Wikipedia, as like a way uh, as a publicly viewable space where everyone can like keep track of their documentation. So to access it, go to frugalscience.su.domains and we'll email this out. Um, and then the first thing you're going to want to do is register. Um, yeah. Um, so I'm sure you're all familiar with something like this. It'll probably send you like an email code to fill out, but I'll just log in with
And I think one comment is trust is very important in our network. So please use your real names just so
yeah.
that I think internally and in general work that we do, we attribute it to people that engage with. So it would be hard to figure out if you've used some
Yeah.
cryptic name.
And also right now, the access settings are such that anyone who's registered can edit any page. Um, so just because uh, to leave like the flexibility for that. That also implies that we're trusting everyone not to like screw with things. And if um, there's like version control built in, so if you mess something up by accident, don't worry, it's very easy to just undo it. And I'll show you guys how to do that in a sec. So when you first go through this, you might want to click here, and this will just um, is like a overview of like how working with like wikis um, happens. And so it has uh, a unique like syntax, but it's very easy to work with. Um, so right now, there's three main pages. One is for member bios, and so everyone can just like write a little bit about themselves. So we can, because it's a big group globally, so we can all get to know each other a little bit better. To make a page for yourself, what you can do is just write your name here, click create new member bio, um, and then it will bring you to a new page. And so basically everything in wikis is just a page. And so if usually what I like to do is like this will create a header. And so um, just like that. And you can click preview and see what the page will look like. And it'll look like that. Um, Up here, you can add links. Here allows you to add links to other pages in the wiki. You can add external links. You can also add upload pictures if you want to upload a little picture of yourself. But yeah, it's very bare bones, but it will get the job done. So now, when we go back, the new person has been added to the list of members. If you ever just want to delete a page, all you have to do is edit it and just delete everything on it and click save. And then the page doesn't exist anymore. Let me go back and that person is gone. But now we have Manu. Um, so there's member bios, there's group projects. The process is exactly the same for making a project, but right now we don't have any of those. And the last bit, which is most relevant for now, is the ideas board. Um, so we have a bunch of different sections. Um, if you want to make a page under a specific section, you can just select um, one of these here. And to get started, you can just click on template, go to edit here, copy everything, Um, and then go back to ideas, new idea, and ecology, and then paste, and then fill it out with all your stuff. And so it's, yeah, very bare bones, but I think it should be able to do everything we want to do. Um, there are a a bunch of other little features that you can explore. But I guess one thing to keep in mind is here, this little older versions button. Right now there's only one, but basically it logs a version of every time you hit save. So if you ever want to just undo something, you can find the version you want and restore it here. Um, yeah, what else is relevant now? Does anyone have any questions at this point? It's fairly,
Yeah,
yeah,
Alex,
just,
if you just
yeah.
unshare for a second,
Mhm.
and one important thing would be is either Alex or Enrico, you guys can copy and transfer some of the older idea boards. I'll give you guys access to the 2024, 2023. It's nice to
Mhm.
be able to get people kind of starting to think,
Mhm.
but yeah, so I think Enrico, you could take that on. For people that are posting things on the idea board, remember the more you write and the more you structure it, the better chance you have of recruiting team members. The more thoughtful you are. So, hysterectomy was a great example yesterday. I went back and read about that problem and kind of better understood the context. But I don't remember who was that you who was the person who brought up hysterectomy last Tuesday? Can you guys remind me a name?
Anjana?
Anjana, yes. Yeah, so I think kind of that's the it's so think about it that way. The way she posed it, the way she structured the idea, suddenly kind of clicked that I went on and did the kind of work that I wanted to do to better understand. So use this really, it's very important. This is not an assignment. This is your probably your chance of recruiting like-minded people to ideas you care about. So, I mean, one template is good, but you could use many other ways to structure as long as you are keeping the problem, at the heart less so on the technology, but if you have ideas of how to tackle and how you're thinking about it or what the ideal tool might be, you can do that. And then we'll have a separate Fred Park that we'll do, which will become very specific. And then eventually we'll add that. Alex, we can add files, right?
Yeah.
Okay. So then everybody can just do Excel sheet for a Fred Park, for example. And I like using Excel sheets because you can also do a lot of numbers in there. You can really attach. We can create a Fred Park template as an Excel sheet as well if somebody needs it, but you can all just make that your own. Um, and Monday is when we'll kind of be going through this in great detail and at that same time, both for the idea board and the Fred Parks. Has anybody started a Fred Park that people want to share before I jump in? Anything else you want to mention, Alex, on the wiki
Um,
side?
no, I think yeah, feel free to like
Oh, resources. Yes. So, Alex, can you be
mhm,
in charge of filling some things around the resources side? So,
mhm,
we have a machine shop that we can make accessible to people. There is a machine shop in the teaching BioE space. There's a lot of other resources that are accessible. And then, Enrico, one thing you should populate is, as I had said before, there's a lot of, maybe I counted last night, there's roughly around 17 or 18 platform technologies that we have built in the last 15 years. They're all accessible for you to build on top. So if you are thinking about imaging-based diagnostics, Octopi is the place to start. If you're really thinking about imaging and oceanography, Planktoscope is a place to start. Not that you have to build on top of it, but at least you have something. So what I'm going to try to do is at least, Alex, link the pages for the Frugal Science page in our lab website and then effectively the papers that are associated. I mean, Friday, I'm noticing that not everybody is attending. And I just have to say this very plainly, you're missing out. if you miss the Friday demo sessions, it's a huge loss because you suddenly get access to this incredible tool that you can build on top of. So, but again, I think I understand schedules can be complicated, but please try to make an effort if because it's the first hand and many of your projects will be shaped by the sets of technologies that we'll talk about. So resources is one, and then Enrico, you could do the linkages for all the projects that let's call them platforms.
Okay.
And then if other people have ideas, I mean, these platforms don't have to be from us. Serena might have access to an awesome platform at Hui, and I know somebody at Hui has built a low cost windmill. I don't know how low cost it is, but a windmill that can be deployed anywhere. It goes in a backpack and you can use it. I think when Enrico and I were there, we were super happy to see and find it. You carry it in your backpack, you open it anywhere, and you can power your sensors with it. So when Alex was in Patagonia, he could have actually been running all kinds of sensors, but literally it's a folding windmill. Super awesome platform. I can write to a set of people, but let's list out. So if you know of platforms that are valuable, I mean, so far is another example. It's a company in Bay Area that makes buoys with solar panel and data transmission. So anybody who's working on low cost sensors like Enrico, we have a simple chance. We have a plug-in board. You don't have to build a buoy. There is another example of an open source CTD in that space. So there are all these sprinkled things, and it's different from a solution. It's platforms, is in the fact that it finishes a core focus or a core goal of an idea. So one piece is checked off and is done. There is a similar framework, for example, if anybody is interested in designing RDTs, there is an open source platform for designing and printing antibodies. So we will do our effort, but I think collectively, let's identify platforms and then I can edit them to just see whether they are a good fit for us or not. I think they have to be open-minded. They don't have to be open source as in free as in beer, but they have to be open-minded that they are the right. I mean, of course, Raspberry Pi, Arduino's, Microbit, all of them actually count. Okay, any other ideas of what we should put on the wiki?
I just want to share one like detail for like
Go
working with
ahead.
the wiki.
Yeah.
Yeah, give me a sec. Um, so say you are you have a project and you want to add more like sub pages to your project page. The way you make a new page is so now I'm editing the main page and now I want to create a new page for resources. And so I just do this and the new page is going to be called resources. Um, the name before the vertical line here is the like behind the scenes name, and then after will be like how it will show up on the main page. And so do that. And I think you can also do this just by linking and then typing a new name, but hit save. And now it shows up, but it's red. And it's red because this page doesn't exist. And then like here you can create it. And so yeah, it's very yeah. So it's a little awkward, but it's you'll get used to it very quickly.
No, I think I actually like its simplicity in so many ways. I think sometimes
Mhm.
all these platforms and everything, it's a little too much. And again, just uh, all kinds of tools are getting accessible at this moment, but you're also just realizing that we are trying to create a resource that will exist for longer periods of time. So it was just the right moment to actually transition to something open. Okay, let's switch topics. I'm going to cover a couple different things today. So anybody wants to pick up a Fred Park as a test case? You want to have everybody critique it, drill holes in it. So I know who's done the most amount of time that you have put in your Fred Park that you're willing to share. Anybody? I just want to make sure so that you kind of are ready for what we're going to do on Monday. But again, remember, this is essential for you to choose projects. So it's actually very valuable to get feedback now. And because we got cut off in time yesterday, I just want to choose somebody, anybody who's even started it at all. I'll give you guys a few minutes to feel bold. You could literally do it also real time. Who wants to volunteer for a new idea? Uh,
Do we
kind
have
of ideas that we haven't discussed so far. I think we haven't covered many threads in oceanography, so I'm curious, or environment. Anybody more on the environmental side? I think there are newer, different challenges that are associated. Anybody wants to propose? I mean, let me ask you this. Do you all know? I know some people were not here on Tuesday, so you guys should listen to the lecture. Do you all know what you're writing your Fred Park on? Who has not as yet decided what they're writing their Fred Park on? Who's totally undecided? Serena is undecided. Who else is undecided? It's perfectly okay. There's no, it's just, it will, remember, the Fred Park doesn't have to be your final project, but it is worthwhile to just choose and commit something and dive in. I'm much more interested in teaching this process rather than the final products per se. So everybody else has decided. So can I pick a random person and have them talk? And I like picking people who don't talk that often. So Apurv, I have not heard from you. Why don't we hear you describe your Fred Park briefly? And then you could just do a quick intro.
Yeah, hello. I'm Apurv. I'm from University of Waterloo, and I work on carbon capture using droplets sliding on thin vertical fibers. I haven't attended last few classes, so I haven't researched enough, but I would like to do Fred Park on basically monitoring microplastics and their impact on planktons because
Hmm.
I have watched few videos where I have been seeing that uh, lots of planktons eat microplastics now, which will affect small fish, big fish, and then in turn us. And
Hmm.
we are the ones putting microplastics in the sea. Uh,
Yeah, so
so
let's
I guess
take that example. I'm very happy somebody brought microplastics. Last night we had a big meeting with a Brazilian group. Uh, I think I had mentioned to some of you, we've been collecting some deep sea fish to monitor accumulation of microplastic because we know a little bit about microplastic accumulation in fish that we eat, but there are other biomes in which microplastic is accumulating that we don't monitor. And that happens to be the midwater. The largest biomass of fish is actually not on the surface, it's in deeper waters. So I had a meeting with a collaborator for one of the expeditions coming up, and I was quite surprised. They already have preliminary data. We have a lot of fish in the lab that we've been collecting from the deep sea. And one of the context is that this chain is quite important. So let's build a Fred Park around it. So what would be the functional requirements, Apurv?
I mean, the monitoring tool has to get samples from deep sea if we are focusing on deep sea.
Yeah, so I think I like the fact that suddenly you picked a subcontext. The ocean is too big. All technologies, like what you do on the surface is a very different. Majority of monitoring currently happens on surface called, these are nets called mantas. And so the Mediterranean, for some of you who haven't read this, Mediterranean is the most polluted ocean in the world in terms of when it comes to plastic. It's obvious because it's closed by cities from all sides. It just circulates, so it keeps accumulating over time. Uh, so the functional requirement would be is we are interested in sampling in deeper waters, for example. The other functional requirement would be is cost per unit area or volume. So you might want to say if it's a monitoring system that you want to be able to, because again, data points can be expensive, so you have to put something. Then the other functional requirement is, do you want this to be a time series or you want it to be a one-off surveys that could be done globally? right? Which would be completely different. So you can write down two different Fred parks. One is an autonomous time series. Another one is something that's driven by a single shot, but it's much more comprehensive. In a time series, you're choosing a specific location. In a comprehensive, you're building a tool that is driven by just what's accessible and you do transits. What are the other functional requirements? There is an obvious one, which was kind of clear in when Vedant had used his thing about PM 2.5. Oh, go ahead. I see, Trevon, your hand was up. Go ahead.
I
It's very
remember
hard for
yesterday.
me to see in the back in the class, so just shout out, or Enrico or Alex can ping. Yeah.
I remember yesterday you said cost should be like in the functional requirements. So like
Yeah.
maybe having this technology be under $10 or $5.
Yeah, so I think it's very important to think about cost. Don't try putting a cost so quickly. Do the analysis because what might sound right, because we haven't as yet defined the technology per se. So it might be, say, $100,000 instrument that you build, but it is capable of autonomously circulating in the Mediterranean and collect massive amount of data. And per data point, you have reduced the cost extremely, like three orders of magnitude. So it's a little bit tricky to what are you putting a price point on? I think so. The way in this case that I would put is the value that we're trying to derive is per unit data point, what is the cost? And right now, I don't have a good intuition for which way we will go, so it's hard to put a number on how much would an instrument cost to be able to do this because we haven't as yet decided whether humans would be involved or not. I see another hand at the back. Go ahead.
How exactly like you're gonna measure your sample or whatever, or measure what you're trying to reduce or
Exactly. I think the big missing one is the size of microplastic. Who gets to define what microplastic is? Remember, there are bottles of your milk bottles floating in the ocean, and then there are nanoscopic plastics that are floating in the ocean that can literally be hundreds of nanometers, and everything in the middle. So it's not good to say microplastics. You have to choose a range, very much like what we did with air pollution. So we would choose a very specific range. I mean, Apurva mentioned the interest was in what can be taken up by plankton. That already defines a size. So I would put it between a slightly on the smaller side, say 1 micron to 100 micron. And that's actually much harder to do as compared to 100 microns to a millimeter from an imaging point of view, because the volume is quite tricky to think about. There's lots of things where you can handle, and it's a very tricky problem because you can calculate the dilution ratio and you know how much volume you have to actually process. So this is a non-trivial problem if you want a very comprehensive measure. Apurva, go ahead. Oh, I think Camille's hands it up.
Yeah, I just wanted to add a couple things to the
Yes.
conversation we're having right now. When you're talking about microplastics, you are correct. It's typically a size, and it's usually folks love to do stuff extra, but it's usually less than 5 millimeters in sizing. And then depending on what type of communities you're working in, these microplastics can get caught up in like living organisms that you don't necessarily want to include. So that's something that also should be taken into consideration for a project like this. You don't want to have it be something like when you're trawling, right? And you're just removing everything at the bottom, even though you're only looking for specific organisms.
Yeah, so I think Camille, I mean, one way of doing that is what we're interested in is writing the functional requirements. So I think one important factor here would be is emphasizing this idea that we are after plankton. And so in the functional requirement, you can narrow your problem, which will also make it quite interesting because there is some amount of work that's been done in people trying to detect raw plastic. But what's interesting in the question that Apurva asked is what is the uptake ratio? What is the uptake ratio when the biology takes in the plastic. And it might be that there are certain types of plastics that are delicious. I mean, delicious is a qualitative word. And then there are other types of plastics that most organisms might not ingest in some way. There could be surface modifications around them. So it would be interesting then we completely focus on trying to identify this ratio. Abundance of plastics and abundance of presence in plankton. Suddenly there, I can clearly see a very clean Fred Park, a path to success. Oh, go ahead, Serena.
Yeah, I was gonna say, like, in addition to just for this question, the like size range for the plastics, plankton is very wide size range as well. And
Yeah,
correct me if you're wrong, but I'm guessing like this is a really interesting question. Part of it is because you're thinking about this is the
food
bottom of the
chain.
food chain, right? And this is how
Absolutely.
things bioaccumulate. So, but are we looking at phytoplankton, which then you might be like things scale, right? Like I guess if you're looking at phytoplankton, you'd be looking at even smaller plastics probably.
Yeah.
Or if you're looking
Yeah,
at
I think
zooplankton because they're
my
filter feeding.
yeah, my intuition was including the zooplankton and including the
Yeah,
heterotrophic pathways
yeah,
because they are the ones that are more likely to
really.
accumulate.
Ingest,
Uh,
yeah.
And then, I wouldn't want to leave marine snow out because marine snow accumulates plastic. We have plenty evidence of that. And then that marine snow is eaten directly by fish and other things too.
Hmm.
Uh, so I think one way of thinking about it is explicitly accounting for this food chain idea. I think what is very
Yeah.
interesting in this process is being anchored in the food chain side of the story. So that gives us functional requirements. Now comes in terms of the kind of design, we've already started thinking about the design. For the cost to work, you have to sort of, some design parameters can be how much volume of water do you want to process in how much time? Because if you don't process that much water, you have no shot of actually finding anything. So a design parameter can be really thinking about very large volumes of water in a short period of time. Oh, there's a question from, oh, is that open Zoom? Enrico, can you mute 1, 2, 3, 4, 5? Unless
Sure.
1, 2, 3, 4, 5 has a question. Okay. Uh, Other design parameters. What are the other design parameters that come to mind? Now we are starting to move towards a solution in this space. What else would you want? Actually, I mean, an interesting one, it's not a necessity per se, is it could be that you might want to characterize the type of plastic because remediation and its toxicity. So, in your sensing capability, it's possible to actually identify what particular plastic, because then there's different buoyancy that is associated with different plastics. So, they're found in different depths of the water column. There's also all kinds of distribution that happens. But that could be an interesting design parameter that you might want to know. Is it polystyrene? Is it something else? What are the other design parameters? Anything else? Things that move you towards a solution. Yeah, go ahead, Ayan.
Uh,
I was sorry.
Oh,
I
go
was
ahead,
thinking
go ahead.
that maybe even reusability might be important
Mhm.
and bringing that like it should be something that doesn't create excessive waste every time you use it.
Yeah, so I think the way I would frame it is lifetime. Like, just how long are you building a one-shot mechanism, or are you building something that will last a certain amount of time? And that will be part of the cost. If I build an instrument that I can install somewhere in a river that's going to last 10 years, then I have the capacity. It can be $10,000, I don't mind, but there is a sense of time frame to it. Versus you could be building a citizen science kit that is a one-shot kit. It's a filtration kit. People around the world go, collect some water, filter something, send the filter to a centralized facility. Now that's a one-shot. It's much more based on citizen science. So you suddenly see I've kind of forked out the design parameters would be completely different between. So the time of use and autonomous versus non-autonomous nature for that would matter. Camille, go ahead.
Yeah, this is just another thought too.
Yes.
When we're talking about plastics, and I love the water. I love marine science. So I spend a lot of time in the water. So unfortunately, I've seen a lot of plastics in the water. But when
Yes.
plastic is in water, it actually can have like a reaction that is amplified when it's the sun is like around.
Yeah.
And so I'm wondering, like, just when you're talking about this citizen science, if we could do something almost like a pH like strip, right? Where you can detect how much microplastics or plastics are in this
Mhm.
space, because that will give you like a real time. Oh, snap, we know there's a lot of
Yeah.
this chemical that we know is caused by this reaction when
Yeah.
microplastics and
Yeah,
plastics
I
and
love
fluid
I love
together.
the direction that you took this thing in. So this is what I want to say. When you build your Fred Park, it's a structured way to brainstorm. So what just happened here is Camille came up with an idea. Why worry about individual particles? What if there was kind of like the equivalent of eDNA, but not eDNA? This is a chemical byproduct. Imagine that there are byproducts like dyes. There are, I mean, pH is one example. There are small molecules that are released from plastic, and we are just running a reaction, and that we could correlate back to the amount of total plastic present. This could massively reduce your cost. Why? Because small molecules diffuse. And if they diffuse, you can make this assumption that they are more homogeneously distributed rather than the heterogeneity of the small plastics. So then you don't have to worry about a massive amount of water. This is absolutely fantastic. I hope Ian or Tambe, Apurv, you're taking notes and you're writing all this down. But
Yes.
all I'm trying to say is please start this process, do this sooner, and you will find it's a very powerful way to structure your ideas and make you go into and do it in groups. Don't do this alone. The reason I enjoy doing this together is the fact that you'll find suddenly we are building on each other's ideas. So quickly gather together people to say, hey, I have this Fred Park idea. Do you want to spend 10 minutes with me? Let people poke holes at it. I have 1, 2, 3, 4, 5 hand up. You have to tell me your name, and it's helpful if you write your name in your Zoom. But go ahead. I see a hand up. Um, okay, maybe.
Yeah, no, I think he can unmute himself, maybe, or
Okay, yeah,
themselves.
I think you have to unmute yourself. While we are waiting, let's move to the next bit. So we said things about design parameters. Design parameters are starting to anchor. Oh, go ahead. I see the unmuted now.
Can you hear me?
We can hear you now. Yes.
Okay. Thank you. My name is Agay. I am from Ethiopia.
Yes.
And I would like to say something about my question is that there is some mycotoxins are very highly infected in food particles, especially in the cereals and also other products. But we consume it, for example, in red pepper, we consume it more than 3 times per day, and there is highly infected with aflatoxin, which
Uh-huh.
is carcinogen. Yeah. So, but to detect this one, it needs a high HPLC, and it's too expensive for,
Yeah.
and it's not affordable.
Yeah.
So, can we use another options like as a simple detect this one? So this is my
Yeah.
question
I,
that
I absolutely love this sort of a puzzle and a question. You should build a Fred Park, build a page on this. I mean, I think it reminds me very much of the work that happened in turmeric, where lead chromate was showing up, and that led to a massive amount of lead poisoning. The
yes,
conventional way people were actually testing for lead in spices was through X-ray fluorescence. X-ray fluorescence is super expensive. It is an X-ray gun that's actually used, and you measure the scattering, and from that you can detect elemental analysis. But what would be useful is to write down explicitly what chemicals are actually known to be found in pepper, and then we can build a portfolio of other sets of tools that quantitatively measure it. And I think this applies more broadly. So when you're writing this Fred Park, you can explicitly state that this as a tool would be applicable to many other food products.
Yes.
I mean, I think there is accidental adulterants, there are on-purpose adulterants, so it's actually useful to choose one very specific one. Okay,
Yeah.
so I think I want to jump to finish kind of the other aspects of this. Now, the next column is analysis. And then what you want to do in analysis is to prove that something that you said around your design parameters is correct or not. So analysis is really at the heart of your work. You might be running a simulation to demonstrate a clever way to collect plastic. You might be running a calculation. You might be running an actual experiment to show whether a set of technology or an idea that you've chosen actually detects different kinds of plastic. So analysis is literally what is the work that you need to do starting tomorrow to make any of these things to be true. Because up till now, in functional requirements and design parameters, we've just been sitting on our couch and we've been coming up with stuff. Analysis is when it all meets the real world. So it's not something that you would do immediately, but you would want to write down what is the skill that you need and what very specifically, what is an experimental design that you could do to prove that this framework would actually fit with the functional requirements. So that can be, by the numbers is a type of an analysis. Simulations, numerical simulations are type of analysis. Experiments very directly prove or disprove your idea. And then the other part of this is it's valuable to think a little bit about expanding it, even if, there might be certain types of analysis techniques that are not accessible to you at that point. That's okay. Somebody else can actually do that analysis. So analysis is a little bit of the evidence that you bring to the table. And so, for example, for the reagent that I forgot your name again, I'm going to just call 12345 until you change your Zoom name. Uh, for example, analysis might be you take the HPLC data and you ask yourself a question, what is the lowest concentration that you still need to detect? And you would write that down as your key because with HPLC, you might actually be getting a number out of it. So
Okay.
it's valuable to think about what you might want to put. And, if, for example, in this particular one, there is a kind of a sensitivity that's already recorded with HPLC data, you can go back and use that as your benchmark to say any other technology I develop has to cross that point. Okay, and then the next after that is risk and countermeasures. Risks and countermeasures are pretty straightforward. The biggest risk often enough is, I mean, one of the big risks is not doing something. So uh, it's important that, you can imagine all kinds of risks, but then there are other things that ideas fall flat all the time. If you can predict it a little bit, it's useful. But risk and countermeasures evolve as your project evolves. So, because you will have an idea and you might think that you could lower the cost, and it turns out that you're not able to hit that benchmark, then that's a risk that you have to come up with another countermeasure around it. Uh, there are much more fundamental risks sometimes in scale where you might have relied on citizens as an approach to build this map, and one of the risks is not getting your community energized enough. So you don't really have enough people that deeply engage in the process. I mean, that's an interesting risk. That is a counter to thinking about building an autonomous system so that you can remove that risk. So whichever way you go, it's valuable to write them down, and then risks and countermeasures change all the time. And then this Fred Park is a living document. It's not something that's fixed. Um, okay, so that's all I want to say about Fred Park. Any last minute questions? And on Monday, we will be taking a close look at the Fred Park itself, and we'll be spending time walking through some of them. If you all can post something earlier, then Enrico, Alex, and I will go through. And then again, everybody should read everybody else's Fred Park. Because remember, this might be the moment you decide and jump on a team to say, this is the most awesome thing I have read. I really want to join this team. And
Can I just emphasize some things?
yes,
Yeah.
go
So
ahead,
I
Alex.
had to do my senior capstone project, and I remember being very finding them like oddly challenging, just like having a lot of paralysis when getting started. That paralysis for me came from like thinking like, oh, like I should write down like the right thing for each section, but there really is no right thing. This is when you're for your project, you're trying to go from something in your imagination into reality, and in your head, everything is works as you imagine it. And all the Fred Park is a tool to force you to think about all the little things that are different between the happy world in your head and like the physical object in reality. So there's no right answer. It's just a tool for brainstorming. And like Manu said, it's 100 times easier if you're doing this as a conversation with someone else. At least for me, like I have a hard time just like coming up with stuff on my own. So definitely work with others and try to just like challenge yourself to have as many like rows as possible just to like get yourself just like brainstorming. If you're like doing stuff with sticky notes, you just want to get as many sticky notes as possible. And then you can always go back and trim things if necessary.
Yeah, I love that comment, Alex. I think both because it was a very practical that when you were building it, and really just I think it's beautifully said. It is a tool for turning your imagination into reality. There is no right or wrong. It seems like it's a kind of a hard engineering tool, but it's much more of it's a thought process tool. But it's also a way to have conversations with people because when you share it or when you do this in a conversation, so I think maybe my proposal would be is that the Ashoka team gets together and does Fred Park all together in the same room. Similarly, for the Stanford group, if you guys just collect yourself together and sit around the table, we can do that this Friday. Try forming subgroups that you really do have. Everybody spends a few minutes doing something on their own and then just get started. And it's an infinite canvas. So don't think of it as like, I have written 5 things. To truly solve a problem, you need like 30, 40 ideas. So it's going to be ever expanding and then we will contract it. But if you didn't in your mind go through the expansion phase, you will get stuck with your favorite thing that you like and it might not be the right approach. So kind of use this also as a funnel. You're allowed to expand. It's perfectly okay that there are certain sets of ideas you will have no notion of how to build the analysis pipeline for it, how to convince yourself which one to prioritize. That's okay. Somebody else will come in. And I think once you guys have populated it a little bit, we will all go through them together to make sure that we filled in some of the gaps. But the more work you do now, the less work will happen. I heard that there is some space now accessible for the Ashoka team, so you guys should spend some time together on this as well. I would love to see a room filled with lots and lots of white paper with all kinds of Fred Parks written and pinned on the boards so you can come in and physically interact with them. You guys can use the same room, the conference room that we have. We can book this for longer periods of time. But I think it's very well said, Alex. Um, okay, I'm gonna now quickly do a premiere on something about diagnostics. I want to spend just the next 10 minutes on a project that we developed that's now scaling up. And then, Alex, one thing I was thinking about for this Friday is to give group a little bit of a teaser for the power of 3D printing, utilizing Inkwell as a demo. So I'm going to ask Anesta to do an assembly for Inkwell. I'll talk through a little bit of this word that I'm calling Inkwell for a second. And then Alex, you can just do a little bit of talk through people about what does 3D printing. I'm assuming everybody is here familiar with it, but you might not know the nitty-gritty and the details and the cutting edge of what's happening in 3D printing and how powerful it is in terms of realizing certain sets of things. I mean, I was shocked to read very recently there are resins now that you can literally print optical elements. Suddenly, optical elements could be 3D printed. And I mean, that's super exciting because you can now design optical things. They're not as good as glass, but it actually pushes you in thinking what's possible. And I'm going to share Inkwell and a little bit of the history of where it came about. And on Friday, we will bring it so you guys can see. Uh, and let's see if I can pull up a deck to show you all. And I'll go through this briefly, but then you guys will all get the chance to see it in person.
My شاي على مرش شاي أمري.
Enrico, can you
Sure.
mute for a second? I think 1, 2, 3, 4, 5 still is open. Okay, I think this will do for right now. So let me dive in and just do a quick review of this as a tool. So just before I start, I think a question that we had been asking in the lab is from medical device point of view, it's this tricky thing that 3D printing has a beautiful analogy to distributed manufacturing, but there is also challenges in what you can actually share and how do you ensure quality and how do you ensure that the designs really meet the criteria of what you're actually interested in. So it's a little bit of a tricky question. In many other fields, it's a lot more easier, but when it comes to diagnostics, quality perturbations can mean a difference between you not being able to diagnose somebody. So we explored this notion in a context of sample preparation. Everybody remembers octopi briefly. Uh, some of you got to see it in person, but I'm assuming some of you know octopi. We built octopi for diagnosing malaria, and kind of one thing that I just want to mention. Uh, I've talked about malaria a couple of times. We think quite a lot about malaria for a very simple reason, is that the number of cases for malaria have been rising steadily. Like last 2025, the number has reached around, 650,000 deaths. And the actual number of malaria cases has been rising dramatically. So malaria diagnostics has been a big portion for what we do in the lab. Uh, the prediction is half the world's population will be or is already in risk areas. This is the tool that we've been building. You saw that tool, but I'm going to talk about where we hit a glitching point. Uh, I think one important thing to understand is that this is one example of one of our field sites. I don't know if I remember sharing this, but this is malaria diagnostics happening in a rural area in India. You're seeing two of the diagnostics person, they're spending hours and hours on microscopes. So we decided to build a completely new framework for doing this using autonomous instruments. It's also important to note that the WHO gold standard for how we make smears in microscopy is actually from 1904. So it tells you how little we have changed sometimes in some of these most critical problems in the world. So this was the tool. You've seen some of it, so I'm not going to spend too much time on Octopi. I'll come back to Octopi at a later time when I do an imaging side of the story. But we were doing these image analysis and then we hit a glitch. we installed this instrument in some of our field sites, and we were starting to see a lot of variation. I'm showing you a data set in which we can now watch every single cell. In a rough drop of blood, there is roughly around 20 million cells. And we hit a glitch that many of the slides didn't look like this. So this was one of the glitch. This is how some of our partner institutions have to operate because malaria diagnostics is done in all parts of the world. And one of the challenges was this was the slide on the right. So you can see there is a problem with that slide is that all the blood smear is kind of smushed only in one region. The blood cells pile up and we realize we need to build something very simple for this process. So you can see on the right, there is a little portion of what looks good and up on top what looks bad. You can notice that the blood cells have piled up on each other right there. And this is the process for the last 200 years that people have been making blood smears. Actually, show of hands, who has made a blood smear here before? I can't actually see. Maybe what I'll do is any show of hands. No, nobody here has made blood smears before. Some of you might have worked in clinical places, right? Okay, I'm hearing some hands. That's awesome. So, you just saw this process. This process has been operating and working for the last 200 years, but it's a perfect angle, it's a perfect speed. It takes years for people to perfect. And if you want a healthcare worker to be able to make this smear anywhere, it's non-trivial. So that's where we started. And one of the things we asked ourselves, and I think this is kind of an important component of this is what would go in your analysis. We asked ourselves a very simple question. What is an optimal mechanism for generating these smears? And how does this process that we intuitively discovered almost 200 years ago actually work? And I think kind of the reason I'm flashing this slide is because I want you to understand that this is the core of why analysis works. The purpose of this analysis is that I can understand that there can be a mathematical framework to approach this problem through first principles. And the first principles here are that there is a critical angle. This is called the Landau's Levitch regime for thin film coating. And in fact, if you have ever painted, you know how fast you move your brush stroke determines how thick you get the paint on your canvas. So now the question was, we understood this regime mathematically, and we started building an instrument, first of all, to test the process. So this is, again, another analysis. This is Anesta and Jerome in the lab. And what we did is we put a high-speed camera right under this process, and you are now watching in real time how the smear forms. So did you notice what just happened? There were blood cells floating around, and then they suddenly come and land, and now evaporation occurs, and then suddenly you have this beautiful image. I'll play this one more time. Right now, the film is fluid. This is when your kind of the edge pass by, and you can now see things floating and kind of landing. So we understood this process a little bit, and that led to this massive phase space of trying to robotically build every possible parameter. Now, this is experimental analysis. And you can see up on the right corner, we're starting to see these beautiful smears. And then long story short, so first of all, we built this using an automated instrument to validate where is the regime of volume and speed that gives us an optimal smear. And so you can see that after 20 millimeters per second, you start seeing these kind of tails and non-homogeneities. And there is a regime in this phase diagram that we want to hit. Now the question is, how do we actually do this in person? And that's when sort of the design process started. And this design process, Anesta is going to show you guys. We needed a linear actuator, and the idea that we came up with is a 70-cent syringe that actually has a little bit of a valve attached to it, is a perfect linear motor. So you can see it's just using gravity. and we can generate a constant velocity motor with no electricity. That's the point, because we want to make a tool that doesn't require electricity. That led to this tool called Inkwell. And on Friday, I'm going to have Anesta assemble one of this for you. Now, this is completely 3D printed parts. And then this is the final solution that we actually built. So you can see it's an object that has a syringe, has a spring, and every single time it makes a perfect smear. So that's 20 million cells accessible to you. It's an object that anybody can print, and it sort of simplifies this entire process. So what's been fascinating is, and then we spent a lot of time characterizing it, and what you will be doing is helping Anesta assemble some of these. So this is the first one we built. It's again, just like every project. At this point, I would say we have reached around 30 to 40 different iterative designs. Uh, and it's kind of an experiment in open source design because anybody else can also modify it. So if you want to really learn good 3D printing principles, this is a fantastic tool to test. And then, I think I'm going to just show you guys the last video that we put together for the assembly. So this is the final version of what it looks like. And it's a 6-minute video. So let's see, I'm going to go faster. So you can see this is the first part, the second part. You will all do this with your own hands. Or I think maybe we'll have Nesta show this for a second. And I'm speeding this all up, and finally the piece comes together. This is all built from parts that are locally available, and I think in 10-ish minutes you can assemble the entire unit. Anesta and Jerome were assembling them in 3 minutes per unit, and then you validate and you test it. But there's a lot of hidden tricks around this in terms of thinking about what goes in the design process associated with this. So this is what we're going to use. This is a preview for what we will do on Friday. I think one thread that's important in this case is it's a good case study in thinking about utilizing tremendous technologies that are accessible to almost everyone. It has a little bit of this flavor of that we would not have been able to tackle this problem if we didn't understand the analytical framework around it. And it also has a new distribution model that we are exploring because we've converted this into an open source model. So there are many different manufacturers that we are now talking to that are willing to build something like this to lower the cost associated with it. And to just give you some numbers, in malaria microscopy alone, roughly 300 million slides are made every year. So that's roughly 500 million smears that are being made like this as a process. So, you know, although it's a simple process, the volumes are massive. And so you can kind of start thinking about this idea of how much data are we leaving behind on the table. Okay, I'll stop there. I know we've kind of run out of time. Uh, Important lesson in this would be is just show of hands. How many of you have actually used a 3D printer before? Where you have gone from something you created to holding it in your hand. So if you've never done that, Alex, this would be our moment. Let's have people walk through. It doesn't matter to me if you just make a little sphere. If you're excited, you can make something more complicated. But please go through this process because what you will realize is that it's a very important step in kind of the prototyping cycle. And this modern day age, there is no excuse that you have to not have gone through this process. And Alex is an absolute master. So there's lots and lots of tricks that you can learn eventually. And if it turns out to be a big component of your project, we will kind of make sure that you master the skill. And so this skill development is critical and crucial. So make sure that you show up on Friday. And then Alex, I will send a message to Anesta. She already has the parts, so we can do assembly. And maybe you can choose one of the parts to print. Or you could print them beforehand and people can just see some of the process. of sending a part to a printer. And my intuition is we can focus on the Pursa if she's using Pursa as one of the core printers. Okay, I'll stop there. Any questions, comments before Friday?
Where is it going to be on that? That's still here, just here. Yeah.
Yeah, and then we are meeting, Alex, you should choose where people should meet you Friday. Maybe in the same space that you're in.
Yeah, I think it should be the same space.
Yeah.
Yeah. And I think, Alex, check with the 3D printer that's also present in the teaching lab. Because, I mean, for a demo, we can do it in our shop, but the idea is to actually use the tools in the teaching space. Yeah. You should also check if Ross has a Pursa. If not, we should ask them to buy one. I mean, it makes no sense to not have it.
Mhm.
Yeah. And then Enrico, can you make sure Alex has access to the teaching lab?
Yeah.
Yeah. Okay. Any comments, questions on what I said?
Yeah.
This is open mic.
I think so.
Go ahead, Ryan.
So in a previous class, I'd mentioned that like if we could have alongside the problem solving aspect of the ideas, if we could also have ideas
Yes.
that that are more like system or mechanism centric, and
Yes.
could we have a space for that as well on the website?
Absolutely. Ian, thank you for reminding me. And frankly, Inkwell would not have worked if I wasn't thinking about how paint dries. And so hidden in that is this framework that I talked about, the mathematical framework for how paint dries. And a lot of people had thought about how paint dries, and only because of that were we able. So there is a hidden physical mechanism for what is called the capillary regime of viscous thin film coating. And that is, so create a wiki space, and what should we call it?
Far from being like confident. You
we
probably
we need a fun name for it. Mechanism is not the right word for it. We need kind of cabinet of curiosity. Why don't you write a space that says cabinet of curiosity, and it'll just be
really
curious
like that.
phenomena that exist in the world.
And I'll help you like.
Yeah,
Does that make sense?
that would be nice.
Yeah, actually, I am so excited about it. I will do it right away. Let me learn how to edit this page.
I think that's what are you by me? Or
I'm design.
Design, okay.
Okay, any other comments, questions?
In the browser, so and for the stuff we're doing, it should be good. Cool.
All right, thanks so much.
Yeah, no worries.
Yeah. I am just creating a page, so.
Oh, this is good. I think we'll record.
Okay, I just created a page for that. So you guys should fill it with all kinds of mechanisms. And I think we will dedicate a couple of classes specifically for that, because, that is when you get to do something that is very different from just putting things together. So Enrico, maybe you can help me. We will populate another page called Cabinet of Curiosity, and we will list all kinds of physical mechanisms, just, make categories around fluids, solids, physical phenomena, biological phenomena, and then people can just post all kinds of fun papers. Things that feel magical in this world and should not feel like you get a lot with very little. That would be kind of the place to put that. They don't have to have a purpose in some sense. And it can be a repository of papers.
Okay.
Okay, I have to run. I got to take my daughter to